Okay, so last time when we ended the lecture, we have a brief start to the chapter of alkenes. So we have learned the electronic structures of alkenes, and also we applied the CIP rule again for the assignment. This time for the alkene geometry, the EOZ system. We also learned the concept of nucleophiles and electrophiles, and we learned how to draw mechanism using curved arrows. And you guys should be able to go to your book, and there is a special section about that, teach you how to draw a detailed mechanism, and there are a lot of practice there. All right, so the stereochemistry drill is still open, but you until October 11th, okay? And the tutorial section starts next week, and you have 3 weeks till the midterm 1, okay? So keep that in mind. At the end of the last lecture, so we are just talking about the the change of energy as the reaction proceeds. Okay, so this is the energy diagrams of a reaction. You have the y-axis with the Gibbs free energy, and the x-axis as the reaction coordinate. Okay, you have the starting material, the product, and the transition state. And the transition state, we also learned about 2 types of Gibbs free energy difference. One is what you have learned in general chemistry, the delta G, which has a small circle on it. That means the energy difference between the starting material and the product. Okay, the new Gibbs energy difference we have learned is called the activation energy. So that's the energy difference between the reactant and the transition state. And the concept of a transition state is especially important in organic chemistry and all the reactions we are going to learn in this course. Okay, so I also showed you 4 diagrams showing 4 types of reactions with different, the activation energy difference and the energy difference between the starting material and the product. All right, so transition states. So I think we have learned that. So it's the highest point of the energy and the partial bond formation and the cleavage. And the activation energy, which is pretty important, is the difference between the reactant and the transition state. All right. So if let's say if you have a ball here, so if you want the reaction to move, so this is the energy. The activation energy is the amount of energy you need to give the ball to roll to the summit of this, which is the transition state. So once the ball reaches the transition state, it can either come back or go forward. Okay, so and because in this particular reaction, the product's energy is much lower than the starting material. So that means if you push the ball to here, it gives enough time, it will go down to your product. All right, so this is where we stopped last time. So for a more complex reaction system, for example, if your reaction has 2 steps, okay, so this is energy diagram of the 2-step reaction. So you have the first step, the blue here, okay, step 1 and step 2. Okay, then between step 1 and step 2, you have an intermediate. Okay, so the intermediate is not a transition state. Okay, in a lot of cases, intermediate can be isolated, but transition states by definition cannot be isolated. Okay, so the first step, let's see, the activation energy of the first step is delta G1 with this sign on it. Okay, it's this amount. And how about what's the activation energy of the second step? Okay, so to do that, you need to find out what's the second transition state, which is so this is intermediate product, second step, highest point here. So this amount, the amount between the intermediate and the transition state is the activation energy of the second step. Okay, so in this typical 2-step reaction diagram, you have a starting material, you have the product, you have an intermediate, which is in between the step 1 and step 2. And then you have 2 transition states corresponding to either the step 1 or step 2. Okay, so in a more complex system, what you are going to see is like this. So you have multiple peaks. Okay, although this looks complicated, but you just need to grasp the several important point of this. Okay, so for example, all the peaks here. So you have a 1 step, 2 step, 3 step. So each step has a transition state, which is the summit of each step. So here, and here. Okay, so B and C. So B is the product from the first step. It is also the intermediate from A to D. So C is another intermediate from A to D, but C is also an intermediate from B to D, right? And okay, there are several concepts you need to learn here. Okay, first the intermediates. I just talked to you about this. B and C are intermediates. Okay, and then the another concept is the rate determining step. So rate determining step by definition is the step with the highest energy transition state. Okay, so the transition state that has the highest energy of the whole diagram. All right, so we just say there are 3 peaks, right? This one, 3 transition state. So the highest energy transition state, which is the transition state from B to C, okay, is the highest energy. So we call that the transition state with the highest energy. So the step that has the highest energy transition state, that is the B to C, right? So it's the rate determining step. So what does that mean? So some of you may have learned those kind of sports that it's called a group run. Okay, so for example, each group have like 5 to 6 runners. All right, and then the time of your group to finish the run is the time of your slowest runner to finish the run. All right, so that means it also applies to the reaction. So the rate determining step is the rate is corresponding to the step that has the lowest rate. So that means is the step has the highest energy transition state, because this is the highest peak to climb, right? So if the faster you climb this peak, the faster the overall reaction is. So no matter how fast you climb this peak, it doesn't matter, because you still have the highest energy peaks here. Okay, so that's the meaning of the rate determining step. The rate determining step is also a very important concept, especially we will talk about some Elkins reactions that really the selectivity is highly related to the rate determining steps property. All right, so a common misunderstanding is that the rate determining step is the step with the highest energy of activation. That is that is totally wrong. Okay, so the highest energy of activation is the activation energy from A to B. Okay, but what you need to because this relative energy difference is higher than here, right? But the true concept is that you need to find the highest energy transition state first. Okay, locate the highest peak. Then if the peak is between B to C, then B to C is the rate determining step. All right, so two steps to find the rate determining step. First, find the highest energy transition state, and then see where the transition state is located. It is located between B to C, so B to C is the rate determining step. All right. Okay, so a concept of catalysis. So as we show you that we can have a very simple diagram. So from this starting material and to this product, okay? And in many cases, the activation energy from the red line here is pretty high, right? So it is sometimes too high that under the room temperature or normal reaction conditions, it just won't react. So there isn't any energy that is adequate to push a ball right through here and push it down. All right, so there is no way in normal condition. But if you have a catalytic pathway, let's say you have a catalyst that is capable of catalyzing the reaction, then the catalyst sometimes operate in a way that has a lower energy activation energy difference. Okay, so if you have a catalyst that can catalyze the reaction in this pathway, the blue one. Okay, you see the starting material is the same, product also is the same, right? But the catalyst has a way to operate in a particular pathway that has a lower activation energy. So it's like climbing a mountain. Okay, you always have the same starting point and the same ending point, right? So you have different routes. Okay, so uncatalyzed routes maybe like this. So you have to climb so high and to get the finish point, okay? But there can be also other, for example, catalyzed pathway that is much lower activation energy. So to reach the same point, you only need to climb a lower hill. So that means with sometimes with a catalyst, you can really climb the mountain much easier. All right. So in a lot of biological reactions, actually it involves catalysts. Okay, and for example, your human body is always in the temperature of like 37 degrees or 36 degrees, all right? And if you have a much higher temperature, like 38 degrees, you cannot even go to the cafeteria, okay? Nowadays, okay? So, so the thing is that a lot of biological system that has enzymes and a lot of proteins that has the catalyzing power, all right? It can make a lot of impossible reactions to happen at an ambient temperature, okay? So you may have seen some chemical factory, they heated the reaction to like 500 or 600 degrees, okay, to make the reaction happen. But the nature makes a human being so efficient that there are a lot of enzymes, instead of going through a high energy activation here, it can go through multiple small peaks, and each has a very low activation energy that can happen under room temperature, okay? So we say enzyme facilitate an alternative catalysis mechanism that allow the reaction to happen at an ambient temperature that would allow the existence of, life, okay? And there are also a lot of difference between biological reactions and lab reactions, especially in organic synthesis lab, okay? So for example, in lab reactions, what we usually use is the solvent, is the organic liquids like ether or ethyl acetate, hexane. But in a biological system, most of us are water, right? So it's an aqueous environment, and the temperature, for example, in lab we can heat the temperature as high as 200 degrees. But for biological system, it's usually very ambient, like 37, 36 degrees temperature of organism. So imagine if a reaction needs 60 degrees, you are cooked. Okay, so it cannot sustain life. And the catalyst, either non or very simple. Or that is not true, because in some organic synthesis labs, some of the catalysts are already very complex. And but in your human body, you have a very complex enzyme that consists of like hundreds of thousands of carbons. Okay, region size usually small and simple, but in biological system, large, complex coenzyme like. Yeah, I'm not very good at this, like ATP, right? So it gives you energy, something like that. Specificity, that's one direction that the organic synthesis or organic chemistry research is trying to catch up with biological reactions. Because in the biological research, we found that a lot of reactions that is very specific and very stereo selective, like enantiomer or diastereomer selectivity. And those level of selectivity, the human being in lab research haven't been able to catch up with. So that's one direction we are going to try to catch up with the nature, or even surpass it, okay, to develop more selective reactions. Okay, so finally we can go to the reactions of alkenes. So the first reaction we are going to talk about is the synthesis of alkyl halide from alkene. Okay, so the net result of this reaction from alkene to alkyl halide is that you see the double bond disappeared, right? But a new bond with H and a new bond with X, which is halide, is formed. All right, so the reagent we usually use to facilitate those kind of the alkyl halide synthesis is hydrogen halide. So for example, HCl, hydrogen chloride, and HBr, hydrogen bromide. So in this case, you can see the electron density here. So we have alkenes, and because it has a pi bond, right? So the red one is here, it's above the pi bond. So that means that the pi bond can serve as a nucleophile because it's electron density here. And you can see the HBr. So HBr, because it's a polarized bond, and the bromide has a higher electron activity. So that means the electron is drawn to bromide. And now, because the electron is drawn to bromide, you can see the blue color is here. So that means the hydrogen now lacks electron density. It needs electron, and you have an electron in the alkene. So boom, it reacts. So nucleophile reacts with electrophile to give you a product. Okay, so a typical reaction is acetylene react with HBr to give isobromide. Okay, so a correct and acceptable way to write a reaction is that you have your starting material on the left with a plus sign, and you have solvent and the temperature will run it. Sometimes we omit the temperature, but to be acceptable, you need to write the temperature, all right? And then you can have your product, okay? And a more simple way and to write it, and a better way to write it is that you only write the starting material you want to focus on. Okay, so you care more about what acetylene becomes. So acetylene becomes isobromide. Okay, and so you put the reagent like the HBr used to be on the left. Now you can put on the arrow, then the reagent and solvent. Then you get your product. Okay, so here is an example in real research. You can see, so for example, we only will write usually on the one end of the arrow, we only write one starting material, right? So 1, 1, 1, 1, 1. And all the other regions of the reaction steps and the regions and the coupling partner or something like that, we write on the arrow. Okay, you can see this is almost a 10-step synthesis to this very complex natural product, which if you are really interested, if you eventually go to an organic synthesis lab, those are kind of the complexity you are going to see, and actually people finish this reaction. So in real lab, so people actually make this, not like us who are just writing down the product, right? We don't need to make it, not in here, but in lab you need to make some of it. Okay, so some thermodynamic data and of the reaction of alkene with HBr is listed here. Okay, so the overall reaction is quite favored. So you can see the arrow pushed to the right. So the equilibrium constant is very high. So let's see this data. Okay, so temperature 298 K, which is 25 degrees, something like that. So delta Ace, okay, entropy is a negative. That means the reaction becomes less random. Okay, what does that mean? So it's very easy to understand. You have the two molecule in the beginning, and you have a single molecule in the end. So the complexity of the system becomes less, right? Because 2 to 1, you have a huge randomness of two molecules. Then at the end, you only have one molecule. The randomness lowered. So delta S is minus. So the delta H is so it means that the reaction release heat. Okay, so that means if the reactions itself is you don't need to probably you don't need to heat it because it's releasing heat. Okay, and then the overall effect of delta G, based on the equation of delta G and delta H, delta Ace, you can see the delta G is minus 44.8 kilojoule per mole, and it's a negative value. So that means the reaction is spontaneous. All right. So here are some key points I listed here. And also, we need to learn terminology. So because alkene react with HBr in an overall addition reaction, okay, because two molecule becomes one, okay? And the second, and the electrophile adds to the alkene. So that means the HBr is electrophile and adds to it, H becomes to this carbon, Br attached to this carbon. Okay, so it's we call it an electrophilic addition. Okay, because they use electrophiles, and based on these thermodynamic data, we can see because delta G is a negative value, so it's favored thermodynamically. All right, so I showed you here more examples about those kind of electrophilic addition of hydrohalide. So HBr we already showed, and hydrogen iodide. Okay, so if it reacts with, let's say, cyclohexane, H attached to this carbon, I attached to this carbon. So this iodo cyclohexane product. Okay, also the cyclopentane, if it reacts with HCl, all right? So the H attached to this, Cl attached to this. okay, becomes iodocyclopentene. But these are very simple examples of this electrophilic addition because these are all symmetrical alkanes, because on the left side of the alkane and on the right side of the alkanes, they are the same. Okay, because you don't have any selectivity issue because the hydrogen, whether it's added to this carbon or added to this carbon, the results are the same because they are symmetrical, right? So, but we have to learn something more complicated, which how about the electrophilic additions to the alkenes that is unsymmetrical? Let's say for this alkene, on the left we have 2R, and on the right we have 2R prime, and they are different. And if the X add to the left, we have this product. If the X add to the right, we have this product. So these are constitutional isomers because they have the same formula, right? And as we learned, the constitutional isomers can also be called regio isomers, okay? Because its direction are different. Okay, X is here, and then X is here, okay? So when we talk about reactions, so we usually call them regio isomers. For example, in here, so when we can say, oh, this reaction, the electrophilic addition, generates 2 regio isomers, okay? And we don't normally say the reaction generates 2 constitutional isomers, but when we talk about 2 isomers without the context of a reaction, we can use the constitutional isomer. For example, let's say on midterm 1, so I listed 2 compounds, and I'm asking you, so what's the relationship between these 2 compounds listed? So you can say, oh, they are regio isomers. It's okay, I will give you full points about that. But normally, just keep in mind, the conventionally, we call it with, if there isn't any context of reaction, we call them constitutional isomers, okay? And this is a detail, this is example of the unsymmetrical alkene, okay? So on one side, you have 2 methyl, on the other side, 2 hydrogens, okay? So people found out that when you do the electrophilic addition of hydrogen halide to these alkanes, like this one, only one, and normally only one major regio isomers is observed, and the other one is either formed in a very small amount or they are not formed at all, okay? So, so what does that mean? So that means that there is selectivity, okay? Because there can be 2 addition outcomes, but one outcome predominates. So that is called a regio selectivity because one major isomer is formed. And in this particular case, this regio isomer has the blue H attached to a CH2. Here, the chloride goes to another carbon. Okay, so and this kind of a selectivity we now usually call the Markov-Nikov's rule because the Markov-Nikov is the guy who first summarized all the results and come out of a general rule to describe the selectivity of the electrophilic addition. Okay, so what does that mean? So in Markov-Nikov's rule, he summarized in the addition of HX to alkenes, the major product results from the addition of the H, okay, the H here, to the carbon that already has more H atoms, and X adds to the carbon that has fewer hydrogens. Okay, so all you need to remember is that the hydrogen adds to more hydrogen. So on the left side, there is no hydrogen left for this carbon, right? Or methyl. Then on the right, it has 2 hydrogens. So the result, if you try to memorize it, is that the hydrogen will add to CH2. Then you give the major regio isomers because the red hydrogen add to 2 hydrogens. And also, of course, the chloride will automatically go to the left one here. Okay, so and the product on this one is not formed, which is the anti-Markov-Nikov product. And the product that corresponds to the Markov-Nikov's rule is called Markov-Nikov addition product. All right. So one thing to keep in mind from a practical perspective. So in the midterm, if I ask you to write what's the product or what's the major product of this addition, you don't need to write this one. Okay. You only have to. If you write this one, you are wrong because I will like count your answer as wrong. Okay. You just need to write the major regio isomers. So in the in description of the exam, I will talk about I will write it on very very clearly. So write down the major product of the following reactions, and you shouldn't write down the anti-Markov-Nikov product. Because we learned Markov-Nikov addition, and then you only need to write down the major original isomer. If you write down the minor one, you are wrong. So another example is methylcyclohexene. So on one side of the alkene, it has no hydrogen. On the other side, one hydrogen. So when it's react with HBr, the red hydrogen will go to the side with more hydrogen here. So 2H here, right? This is the major isomer, the only isomer you need to write down in the exam. Okay, so so for this example, you have one hydrogen here or two hydrogen here. The hydrogen adds 2 more. Okay, this one major. So what if both carbons have the same number of H? Okay, like this one. So on the left side, you have a 1 hydrogen. On the right side, you also have 1 hydrogen. So when it add with do the addition reaction with HBr, so both products will be formed. So there is no selectivity. So okay. So again, in the exam, if I give this compound and add it to with the same amount of hydrogen on both carbons, so because no selectivity, you need to write down 2 products. Okay. Okay. So of course, I'm not going to ask you just to memorize the Markov-Nikov's rule. So, and the reason behind the Markov-Nikov's rule is really, really interesting, and we definitely should learn it. Okay, so but the first, let's just go over some concepts. So, alkene in this kind of reactions is electron rich, right? Because it's red, not because it's red, because it has a pi bond. And it has the electron density here, just showing the electron density map. It has a red electron density here, right? It is the nucleophile in this reaction, and will be attracted to electron deficient species, which is the electrophile, the HBr here. Okay, the HBr is an electrophile in this addition reactions, and this reaction happened in 2 steps. Okay, the first step is that the H will add to the nucleophile to give a carbocation. Okay, so if you draw arrow pushing, the arrow will go from the nucleophile to push here, Kirchhoff bromide. Okay, now the bromide become a anion. Okay, in this intermediates, the bromide now become nucleophile because it has electrons, and the carbocation, because it's an electron deficient species, now becomes an electrophile. The second step is the recombination, where the bromide arrow would go to the carbocation to form this final product. Okay, so oh my God, I just described it to you. Okay, so the electron goes from the pi bond H, Kirchhoff bromide, carbocation, right? And then the addition of bromide anion in the second step to the cation makes the product. Okay, so you may figure out that, oh, this carbocation is quite interesting, right? We have never learned it in organic synthesis, and what's the property of it? Okay, so carbocations is a very important intermediate in many reactions, particularly in this electrophilic addition reaction. So it's planar. Okay, it has 3 substituents, and the 3 substituents is distributed on a plane. Okay, and perpendicularly, it is a vacant p orbital. Okay, this organization is particularly great for carbocation because there is a less repulsion between bonding pairs of electrons. So this is far away, and also the empty orbital is far away from from these substituents, 90 degrees, right? And it's surrounded by only 6 electrons in 3 sigma bonds. So it's not. So because it's an unfilled octet, it's electron deficient. So it needs a pair of electrons to become 8 electrons. Okay. So because these unfilled octet, these carbocation is usually considered unstable, high energy, and reactive. So you can see the different structures between the carbocation and the normal filled octet. Okay, with 8 electrons around the carbon, but here only 6. So and carbocations have different stabilities when substituted with different substituents. For example, we say the methyl carbocation is the least stable one, and the tertiary carbocation is the most stable one. In between is the primary and the secondary. So the reason we named them primary carbocation is because this carbon is primary carbon. Okay, and do you still remember the definition of primary carbon? So the primary carbon is a carbon only linked to one another carbon. Okay, so in this carbon, it's a tertiary carbon because it's linked to three other alkyl group, three other carbons. So it has a tertiary carbon. So is there a quaternary carbocation? No. Okay, so because quaternary carbon is already attached to 4 substituents. All right, the biggest one you get is tertiary carbocation. All right, so why? Why is the tertiary carbocation the most stable, while the methyl carbocation is the least stable? All right, so I'm going to, so the reason is very simple. It's a hyperconjugation. So you may still remember the concept of hyperconjugation as we learned about the stability of alkenes. Okay, so when we explain the stability of alkenes, we have told you that the tetrasubstitute is the most stable because it has more substituents. Okay, and the substituents has the CH bond can align with the pi star orbital, which is the anti-bonding pi orbital, like this one. Okay, and the more substituent it has, the more hyperconjugation like this will happen, right? So at the same reason, it applies to the carbocation. Okay, so let's say this diagram. Okay, so this is empty p orbital, which needs electron. It's an unfilled octet. Okay, it's desperately looking for electrons around it and see where is it, where is any electrons. As long as there is electron, even bonded electron like CH bond, we have 2 electrons within H and C, right? So the p orbital, the empty p orbital really likes it. Okay, so what the CH3 did is that it will align one of the CH bond here, and the bonded the spreading of the bonded electrons will goes to the p orbital, empty one. Okay, then the empty p orbital becomes a little bit more comfortable. Okay, so the reason why tertiary carbocation is more stable because you have 3 CH bonds, and you can have a lot more of these hyperconjugation happening than the methyl carbocation. Because in the methyl carbocation, you don't have a CH3 group. So there is no CH bond, you can align it with this empty orbital. But in the tertiary one, you can. So that summarizes the reason why tertiary carbocation is more stable than secondary and primary, and the methyl is the least stable carbocation. Okay, so this is a more vivid demonstration of the hyperconjugation. You can see this is a CH bond, right? It rotated to this degree to kind of sharing electrons with this empty p orbitals. So so the p orbital gets very comfortable and happy. All right. Okay, so once we learned these relative stabilities of carbocation, now we can try to explain why Markov-Nikov's rule applies. All right, so if you look at this reaction diagram, so that the intermediate here, which is carbocation, right? And a reason of the second step has a very low activation energy. Okay, so activation energy of the first step is this high. The activation energy of the second step is this high, so relatively small, very small actually. So that's understandable because you have a very reactive intermediate, and it's really easily to just recombine with the bromide to give this. So that makes the activation energy of the second step very low. Okay, so this is the second transition state here, and the first transition state here. Okay, so now let's apply the rule we just learned. So can you find the rate determining step of this 2-step reaction? Is it the first step or is it the second step? So you remember the way to find it, right? First, you need to find the transition state of the whole diagram that is highest in energy. So which is this one, right? Not this one. This one is higher. And then you see where the highest transition state is located. Oh, it's located from the alkene to the carbocation intermediate. So that means the first step is the rate determining step. Okay, so also means that the overall reaction rate is determined by this activation energy, because this step is the rate determining step. So if this step is fast, the whole reaction is fast. If this step is slow, the whole reaction is slow, right? So the only thing we care about is the activation energy of the rate determining step, which is delta G1 activation here. Okay, so we already know that the second step is very fast. The first step, the addition step, is the rate determining. Now we have to select between two pathways. The first pathway is that the H will add into the two hydrogens here, which is the Markov-Nikov selectivity, right? So when the H adds to here, the electron grabs H. So carbocation formed at this position, right? Tertiary. So how about anti-Markov-Nikov? That's opposite to Markov-Nikov. So the H will goes to here, the less carbon, less hydrogens. Okay, then the carbocation will be generated at the terminal position, which is CH2 here. So this is a primary carbocation. Okay, now remember. So we just learned that tertiary carbocation is much more stable than primary carbocation, right? Okay, then we got something. Okay, so one intermediate of the pathway is much lower in energy than another pathway. Does that mean something? Yes. Okay, because you may say, okay, so the formation of the most stable carbocation, tertiary, so on the what leads to the Markov-Nikov addition product. Okay, and we also know in the previous slide the ratio of regional isomer is determined by the relative rate of two pathways. Okay, what does that mean? What does that mean? So although we know that the primary carbocation is much less stable than tertiary carbocation, okay, so intermediate wise, so this is much higher in energy, okay? But what we care is not G1 and the red G1 here, right? We just talk about, what we care about is the activation energy. We don't care about the energy of the intermediate, right? We only care about to the transition state. The carbocation rule here is that the intermediate of the tertiary is more stable than here, but not the transition state. Because for now, we don't know anything about the transition state. We only know the intermediate relative stability. Okay, so as I summarized here, so the rate of the reaction is related to the transition state energy, like these two, not directly related to these two. Although we know the relative stability of these two, but that's not what we're really looking for. We are really looking for is transition state, not intermediate. Okay, so what do we know about this transition state? So what's the knowledge we have about this transition state? Can we judge what's a more stable transition state between the red and the blue? Okay, then we need to learn something about the transition state structures. Okay, so while the energy of transition state controls the rate of the reaction, so it is transient. We cannot isolate it, right? So we cannot just say, okay, to see what's the relative stability of these two transition states and compare them, we just isolate them and see their structures. No, we can't, because transition state cannot be observed. All right, because it's in the highest energy species in a reaction, and by definition, it's not stable enough to exist for one vibration, because it's a partially bond form, partially bond break. You touch it, it breaks. Okay, so yeah, to put it vividly. Okay, so what we see is that we have several types of transition state we can imagine. The first is that okay, in the transition state, this bond is partially break or formed, Okay, what if from ABC to ABC, the B is in the transition state is more closer to A. Okay, so in this case, this transition state looks like starting material, right? But in the starting material, A and B are bonded. In the transition state, A and B are very close. How about the other possibility? In the transition state, B and C are very close. okay, it looks like the product, right? Because in product, B and C are directly bonded. Okay, so these are three scenarios of transition states. The first one is the transition state looks like the starting material, AB, very close. So we call it early transition state. And another possibility, another extreme possibility is that B and C are very close. So we call it a late transition state because the transition state resembles the product. Okay, there of course is a lot of transition states between them, like the B is in the middle of it. So it doesn't look like starting material or doesn't look like the product. So for example, let's apply this to the alkene addition. So in the alkene addition reactions, okay, so we have the H partially bond formed with this carbon, and we have the pi bond partially broken, and we also have a HBr bond partially broken. So everything is partial, okay? So this is what we call the transition state, okay? So what we need to figure out is here, is that how do we know this is an early transition state or late transition state? So does this transition state looks more like the alkene, or does it looks more like the carbocation? Okay, then another guy comes out of a rule called the Hammond postulate. So for the Hammond postulate, it states that the structure of a transition state resembles the species that is nearest to its free energy. Okay, so let's look at the red one first. So if the starting material and the product are equal in energy, so you can imagine the peak looks symmetrical, right? So we say the transition state 2 doesn't look like starting material or the product, right? But if you have a starting material that, for example, the green one, very low in energy, the product very high in energy, and when you draw a transition state, the peaks you have to draw like this, and when you draw like this, the transition state 3 is very close in energy with the product. And the Hammond postulate says if your transition state 3 is very close to a product in energy perspective, then the structure of your transition state looks like your product. So what we call is a late transition state because your transition state looks like your product. And if your reaction is exogonic, so that means your starting material is really high in energy and your product low. That means if you draw a curve like this, your transition state will be very close in energy with your starting material, right? And based on the Hammond postulate, your transition state structure will also be like a lot like your starting material. Okay, so now let's go back to the alkene addition. We know that the first step, because the carbocation is so high in energy, so the first step is what we call endergonic. Okay, endergonic reactions. Then based on the Hammond postulate, your transition state will look like carbocation a lot. All right. So what does that mean? It means like the transition state will not look like this, which the alkene structure is partially still there, looks like the starting material. The electrophilic addition transition state of HBr to alkene will look like that the carbocation is already generated. Okay, so the transition state will look like the carbocation product. So it's what we call the carbocation-like transition state. All right, now things become interesting because we know that for example, this tertiary carbocation is more stable than the primary carbocation, right? So, and we also know based on the Hammond postulate that the transition states looks like a carbocation. Okay, then we can say the transition states of the red one is lower in energy than the blue one, right? Because they look like the product, and this product is more stable than this one. So that means this transition state is more stable than this one. Okay, so because the most stable carbocation is formed more quickly in the rate determining step, because as we deduced that this one is low in energy, so this Markov-Nikov selectivity transition state is has a lower activation energy, thus the rate is faster. Okay, so the Markov-Nikov selectivity is not because the reaction favors a more stable carbocation intermediate, but because the carbocatonic transition state goes through, the red one, is lower in energy. Okay, so you need to figure out, so you need to learn the logic very clearly. Okay, so the logic is listed here. So because the red one has a more stable carbocation, all right, and also because the transition state looks like the carbocation, so that means the red transition state is more stable, and that means the step one is faster. And because the step one is faster, and also because it is a rate determining step, so the overall electrophilic addition through the red pathway is faster. And that means if the red pathway is faster, the Markov-Nikolov product is formed. Okay, so it might seem a little, I may talk too fast, but it also may seem be more a little bit difficult for you guys. But just to try to, so for these several slides, you really need to understand it, okay? So when people ask you why the addition of HBr to alkenes generates a Markov-Nikolov product, if you say that, oh, because the Markov-Nikolov product has lower energy carbocation, this is wrong, okay? It does have lower energy carbocation, but it's not the direct reason why it generates Markov-Nikolov product. It's because the low energy intermediate gives low energy transition state, and it is the low energy transition state that makes the Markov-Nikolov addition faster, and that leads to the Markov-Nikolov product. Okay. All right. So there is also some degree of regional selectivity because we have a Markov-Nikolov rule. But if your carbocation intermediates of two pathways differs a lot in energy or differs a little bit in energy, they can have consequences. Okay, for example, for this one, we have these alkenes. So the intermediate, if H added to the terminal one, it's a tertiary, right? And if H adds to the middle one, it's primary carbocation. So it's primary versus tertiary. And you can see as a result, this is the only product. But what if this alkene, all right? So if H add to this one, cation generated here, so it's a tertiary. If H add to the left one, the cation generated at this position, which is secondary. So it's now secondary versus tertiary. So in this case, the result is that although this is still generated in as major product, so this anti-Markov-Nikolov product is still generated, but in a very small amount. But if you have a more drastic comparison between carbocation, like the primary versus tertiary, this is not even formed. Okay, but again, I need to remind you that even if I put this alkene on the midterm, you just need to write down this. Don't write this. Okay, you only need to write the major product. If you write a minor, I would assume you don't understand the Markov-Nikolov rule. All right, just write down the major product. All right, I think it's time's up. So next time we will talk more about the stereochemistry. So it's different than from regional selectivity, because the regional selectivity generates constitutional isomers, right? But the stereochemistry generates products with the same bond connection but different 3D orientation. So it's different from the regional selectivity. And we will learn about the HX addition and more about carbocation, and we will move on from the HX addition to more complex system like the X2 addition and other reactions of alkenes. Okay, so that's so much for today and for this week. I will see you next Tuesday. Have a good weekend.